Hi everyone, welcome back to our channel. Now we are moving to the chapter number 2, unit number 2, chapter number 2, series AC circuit. Okay, in this particular video, we are going to discuss about this particular syllabus and then one part of the video, one part of the syllabus, some part of the syllabus. Here, in this one particular video related to the, in this particular syllabus, are real circuit and quality factor and skin effect. So in this particular video we are going to discuss this particular part. So one video on that. Okay, the second video, RC circuit and coupling capacitor. Okay, this is the second video. So that is a video, one video on those particular topic. Next, third video on RLC circuit and resonance in an RLC circuit, as well as resonance curve and main characteristics of series resonance. Okay, this is for one more video. Next, another video, the fourth one, bandwidth of tuned circuit and sharpness of resonance and tuning, as well as tuning in radio ratio and radio tuning dial. Okay, this is a one more video. At the last, parallel resonance. Fifth one, parallel resonance. We are going to create one more video on that. At the last, conventional problems. Okay, this is our syllabus coverage of this particular second chapter. Okay, chapter number 2. Let us start our discussion now. The first topic, that is a RL circuit. Okay, so let us discuss RL circuit. You know, R is nothing but a resistance, L is nothing but a inductance. Both are connected in series. Let me take, this is the resistance, this is the inductor L. So the inductive reactance, you know, the inductive reactance you can represent it as XL. So those two are connected into AC supply, that is a V. So whenever this AC supply is connected to this particular series circuit, definitely the voltage drop across the VR, voltage across the L is a VL, XL is a VL. So the current flowing through this particular series circuit is I. You know, in the series circuit, current is a constant, the voltage is divided, yes, it is obeyed. So in this particular circuit, we need to know that all the values of voltage and currents are RMS values. That's what here, where in this particular diagram, where V is a RMS voltage. Okay, next I is a RMS current. You know what is mean by RMS, what is mean by average value from the previous discussion. Next, R is the resistance, you know, R is the resistance, and XL is a inductive reactance. Inductive reactance. Okay. Next, I use the current already, you know that. VR is a voltage across. VR is nothing but a voltage across resistor that will be equivalent to IR. Next, VL is equal to voltage across inductor, that is a multiplication of current into XL, inductive reactance. Okay. So in this case, you know, resistance and inductance cases, we know already from the previous class. Resistor, in the case of resistor, voltage and current are in phase. In case of inductor, current is lagging by voltage 90 degrees. Okay, so by using those conditions, let me draw the phasor diagram for this RL circuit. In the examination, they are asking about the phasor diagram of RL series circuit. They will give us different phasor diagrams in the A, B, C, D options. You are able to identify the phasor diagram. So for example, here current is a constant for both the elements. So keep it in mind, current is a constant for both the elements. That means the here for case of resistor, current is a, I am taking the current is a reference because the current is same for series circuit. That's why current is a reference. Now voltage and current are in phase with each other. This is the current as well as this is the voltage. So in case of resistor, both voltage and current are in phase. Coming to the inductor, if you take current is a reference, what about the voltage? Voltage is leading by 90 degrees. If current is a reference, this is the voltage VL, IL. These are the two phasor diagrams. So equivalent phasor diagram of RL circuit, case here, voltage is a reference. Sorry, it is a series circuit, current is a reference, IR, some current. Okay, whenever current is a reference, in case of voltage VR, both are in phase. In case of voltage across the inductor is a 90 degrees. Okay, 90 degrees leading, that is a VL. The vector sum of these two voltages, total voltage is equal to vector sum of VR plus VL. So that's what here. So now this is a V. So this V is nothing but a vector sum of VR plus VL. This is the voltage, angle between the voltage and current is nothing but a power factor phi. Okay, this is the actual phasor diagram of RL series circuit. From the phasor diagram, we are going to draw the impedance diagram also. The impedance diagram, in place of VR, we can write it as a R, resistor. In place of VL, VR, we can write it as a resistor. In place of VL, it is a inductive reactance. The vector sum of both is nothing but impedance Z. It is a phi, phase angle. Here also phase angle phi. So all of it clear about that? This is a vector diagram or phasor diagram of RL circuit. This is impedance diagram. From that we are going to derive some equations. Those are important in the examination point of view. So here the voltage is equal to, just now I mentioned, VR plus vector sum, VR plus VL. Okay, from that the magnitude V is equal to square root of VR square plus, I'm sorry, there is no vector symbol here, VR square plus VL square. What is a VR? VR is nothing but a voltage drop across a resistor, that is I into R. We can replace the here I into R whole square, plus VL is nothing but a I into XL whole square. Okay, here current is the same. Okay, we can take out the current outside. So finally you know r square plus xl square. From that v by I, in case of AC circuit, v by I is nothing but a impedance z. So finally z is equal to square root of r square plus xl square. This is a formula I need to remember. So what is impedance of RL series circuit? Square root of R square plus XL square. Okay. Then you know the current formula. From that, I is equal to current voltage divided by impedance. We can use this formula also in case of you want current. Another important formula here, power factor. In case of AC circuit, in case of series AC's RL series circuit, you want to find out the power factor for this combination. The power factor is nothing but a cosine of angle between. So I will tell you the power factor definition here. Power factor is defined as power factor. Everyone note down. Power factor is defined as the phase angle between voltage and current. Okay, it is represented by phi. Okay, so sometimes theta also, no issue. So from that, power factor cos phi is equal to, just look at here, this is a cos phi. Cos is nothing but adjacent divided by hypotenuse, right? You know the formula from trigonometry. So from that, cos phi is equal to adjacent, that is r by hypotenuse is a z. This is one of the important formula to find out the power factor. Okay, clear? So sometimes tan phi can use tan phi in the normal case. It is not a power factor. Normal case tan phi can write it as a tan phi is equal to, tan is nothing but a opposite by adjacent. So sorry, adjacent divided by opposite. What is adjacent? R. Opposite XL. So this is the formula for tan phi. Okay, I'm sorry. Tan phi is nothing but a opposite divided by adjacent, XL by R. Clear? Everyone note down these formulas. So still now we got impedance value, you got current value, you got power factor value. We can find out the power, right? So the power is equal to power consumed by the resistance or power absorbed by the RL series circuit is equal to, P is equal to power formula I square R. Okay, I'm focusing about the active power here. Active power is represented by P. So in this case, active power V is equal to I square R. We can write it as I into R. In case of I square, I can write it as I into R. So from that, I into I is, we can write it as a V by Z, right? From that, VI into R by Z. R by Z is nothing but a power factor cos phi. Finally, what is the formula for power, active power formula? P is equal to VI cos phi. So everyone remember, these formulas are very, very important. What is the units of power factor? Watts. Maybe in the examination they will ask the question, what is the unit of power? Watts. Okay. So this is about the active power. Maybe in your syllabus it is not mentioned. Maybe in the examination, maybe chance is there they will ask the questions. I will tell you the remaining two formulas also. Okay. Everyone note down. Reactive power, that is represented by Q. Reactive power formula VI sin phi. Okay. Units of reactive power VAR. Okay. Units of reactive power VAR. So that is another formula. Next, another formula, apparent power, that is represented by S, is equal to V into I. Units are volt ampere. Okay, VA. Transformer rating is also VA, volt ampere. That is a kilovolt ampere, KVA rating transformer. So that already in the previous 7th chapter, unit 1 7th chapter, you know that. Okay, still we completed total all the formulas and then RL series circuit, everything I explained here. I hope that it is clear. Right, next we are moving to the one problem related to this particular RL series. Okay, look at the problem. So in this problem, a coil having a L is equal to 0.14 Henry, R is equal to 9.43 is connected across 50 H 135 volt. Okay, these two coils. So here resistor as well as inductor. Resistor is a 9.43 ohms, that is R. Inductor XL you need to find out, they provided L only. Those are connected with AC source of 135 volt comma 50 hertz is a frequency. Clear? Now they're asking about the first point is XL. You know the formula for XL is equal to 2 pi FL. The formula for XL is equal to 2 pi FL. These formulas are already given in the unit 2 chapter 1. 2 pi F is a 50 Hz, L is a inductor 0.14. From that XL is equal to 44 ohms. Okay, what is XL now? 44 ohms. First part is done. Coming to the second part. What about the second part? Impedance. Just now we see impedance is equal to R square plus XL square. What is the R square? 9.43 whole square plus XL square 44 whole square. From that Z is equal to 45 ohms. Okay, you got impedance. Next, current. Third one, current. I is equal to, just now I gave V by Z. What is a V? 135. What is a Z? 45. So current will be 3 amperes. Okay. Next, RV, voltage across the resistance. The fourth point, voltage across resistance. VR is equal to, you know, I into R. That will be equivalent to, I is a 3 amperes, R is a resistance is equal to 9.43. That may be equivalent to 28.3 volt. Okay. Next, fifth one. V, total volt, fifth one, voltage across the inductor. VL is equal to I into XL. What is I? 3. XL is equal to 44 you got. That will be equal to 132 volt. Okay. Next, sixth one. The sixth one is a power factor angle. That is a phi is equal to tan inverse. You know, phi is equal to, just now I gave formula XL by R. That value tan inverse XL is a 44, resistance is a 9.43. You will get power factor phi angle is 77.6 degrees. It is a lagging because inductive load. Next one, seventh. What is the seventh bit? Power factor cos phi. You know, phi value is 77.6, cos 77.6 degrees is equivalent to 0.21. Otherwise you can use the formula cos phi is equal to R by Z. So from that, resistance is equal to, what is the resistance value? 9.43. Impedance is equal to 45. That is also 0.21 only. It is a lagging power factor. It is a lagging power factor. Okay, both are same. Gave the both the methods. At the last, you know, power. So eighth one is a power. So power P is equal to I square R. That is a I is equal to 3. Resistance is equal to 9.43. That will be equivalent to 85 watts. So this is about the solution for this, about the problem of RL series circuit. So don't worry about this particular problem having 8 bits in the examination. they provide the values in the reasonable value. You can simplify the values only. They won't give the ratios like everything you can get cancelled because calculator is not allowed. But your understanding purpose, I took up the problem, I explained here. So in the examination also this type of questions, numerical questions may be present. Okay, still we clear the RL circuit. Next we are moving to the quality factor. So next one, quality factor, Q factor. Okay, the Q factor of a coil. For example, the coil here, inductor and resistor together, it is a coil. Inductor as well as resistor. So quality factor for this particular coil is equal to XL divided by resistance. That is a quality factor. It is a ratio of inductive reactance divided by resistance. You know XL formula. XL is nothing but a 2 pi FL divided by R. So this is a formula for quality factor where L is the inductance, R is a resistance. You know that. So after that, quality factor for different coils. For example, quality factor Q value of a coil, normal coil, the range will be 10 to 1000 in the normal case. In case of normal frequency, in case of RF, in case of radio frequencies, quality factor value, Q value of a particular coil, it may be vary from 30 to 500. Okay, in case of RF. So you know at low frequencies R just equal to the DC resistance. You know this particular case, low frequencies, this R is same as DC, AC value same as DC value, both are same. But in case of higher frequency, it may be present effective value of AC and DC both are different. The reasons behind, we have three effects are there. Why it is different, both the resistance, AC resistance, DC resistance. First one is a skin effect. Okay, I will tell you what is mean by skin effect. So why this difference is taking place? Because AC resistance as well as DC resistance both are different. That's why the reason behind both are different. That is the first thing is a skin effect. The second one, eddy currents. Eddy currents. Third one, hysteresis losses. These are the three reasons we have a both AC and DC resistors are different. Hysteresis losses. Clear? Now my question here, I will explain the skin effect. You know eddy current losses is nothing but a circulating currents already explained in the 7th chapter, Unit 1. Hysteresis losses also explained in the 7th chapter. I don't want to repeat the both the cases. I will explain only skin effect. Clear? If you are not able to listen those classes, just go back to our previous video of 7th chapter. You just complete the 7th chapter. In between you will get the eddy current losses and hysteresis losses clearly there. Okay, now how to measure this particular quality factor? We can measure this particular quality factor with the help of the Q meter. So Q meter used to measure Q value, quality factor value. Clear? Now we are moving to the skin effect. So skin effect. Okay. So I will explain what is mean by skin effect. Everyone listen carefully. I will take this is a conductor. I am operating this particular conductor at low frequencies. For example, the frequency is a minimum value, low frequencies. The current will be flowing with this conductor is a uniformly. That means total entire conductor, the current will be flowing uniformly. Okay, fine. In case frequency is increases, in case of frequency increases, whenever frequency increases, the reactance value increases. Yes or no? Because XL is equal to 2 pi FL. Frequency increases, the frequency increases, XL is also increases. XL increases, I is equal to V by Z. Z is nothing but a R plus XL root of square. Okay, so anyway, XL increases, automatically current will be decreases. So finally here you need to remember that whenever frequency increases, total entire current is uh, concentrated on the skin of that is a surface of the conductor. That means center will be there is no current flowing through the center, entire current will be flowing through the surface, near to the surface of the, that's why skin effect. That means the internally there is no current flowing inside up to here, outer side only current will be flowing. So that means in center, at the center of the conductor, there is no current flowing, it is a wasted, like total entire material. This effect you are called it as a skin effect. So finally skin effect is nothing but a total entire concentration of current flowing through surface of the conductor at center there is no current flowing. There is no current flowing. So this is the reason, this is nothing but a skin effect. In the examination they will ask you what is mean by skin effect. Total entire current flowing through the surface of the conductor, center of the conductor, center part of the conductor, current flowing is 0. Okay. Now I will ask you one question. This skin effect is useful in the circuit or not? Not at all, because whenever you design the conductor, some of the portion is utilizing to transfer the current, but internally surface center of the conductor, total entire material is wasted. So that's why your manufacture halo conductors, in case of halo conductors, so inside everything is halo, but the conductor material only present surface, near to the surface. That means there is no, actually there is no current flowing through the inside the conductor, center of the conductor. That's why you can save the material once you design the halo conductor. Okay, bundle conductors, different methods we have. This is actually concept from power systems. So there is no lot of explanation is there in the power systems, but we are writing the exam for KVS TGT. Small part is mentioned. That's why this particular knowledge is enough for you. Okay. Now we are moving to the one problem going to discuss related to the quality factor. Okay. Now the problem, next problem. So the problem here, 100 microhenry coil, that is a L value is 100 microhenry. The Q value of 100 at 5 megahertz. So the given quality factor Q is equal to 500. What at the frequency F is equal to 5 megahertz. That means 5 into 10 power 6 hertz is a frequency. They are asking about the effective value of resistance. They are asking about the effective value of resistance. The effective value of resistance Re is equal to XL divided by quality factor. So what is the XL? 2 pi, F is a frequency, L is 100 into 10 power minus 6 divided by, what is the quality, what is the Q factor? 500. Okay, from that effective value of resistance is equal to 6.24. So this is about the solution. Okay, so up to this we completed the RL circuit. Next class we are going to discuss about the RC circuit. Thank you.